Hello, everyone. My name is Bhaskaram, and this is going to be a quick video about short noise. So, short noise originates from the discrete nature of electron charge. So, the charge of an electron, we represent it by Q, is 1.602 times 10 exponent minus 19 coulombs. And so, I want you to imagine a conductor, a cylindrical conductor. Well, the shape of the conductor doesn't matter for this example, but I want you to imagine a conductor which has a potential difference. And so we have a DC current flowing through this conductor. Okay, so I have shown electrons flowing through this conductor in purple. And let's say that I'm trying to measure the number of electrons that pass through this cross section per second. So number of electrons passing through this cross section per second, right? And yeah, basically the number of electrons that pass through this cross section per second is basically my current, my DC current, right? And so now I can have, let's say as an example, I can have 2 electrons passing through this cross section per second. I can have 5 electrons. If I increase my DC current, I can have, let's say, as an example, I can have 5 electrons per second that are passing through this cross section, 100 electrons, 1,000 electrons, whatever might be the case. But I can't have 2.536 electrons passing through this cross section per second, or I can't have 527.3729 electrons passing per second through this cross section. And so that's basically what I mean by the discrete nature of electron charge. Each electron has a charge, and you can have 1 electrons, you can have 2 electrons, but you can't have 2.5 electrons or 3.5 electrons. It has to be an integer number of electrons, and each electron will have a certain amount of Coulomb charge, right? And so it's electrons are fundamental particles, and you can't have half an electron. It's discrete in nature, and so that's what I wanted to point out. And so ideally, if you had some DC current passing through the conductor, you might expect something constant. So if I'm plotting IDC, it would be something constant in an ideal case, which is what I would imagine. But in real life, if you zoom into this IDC current, if you zoom into it enough, then what you would see is something like this. So IDC would have like this step kind of behavior, and that's because each electron has a discrete amount of charge, right? And so your IDC won't be a straight line. It would be like step ups and step downs, and there would be a certain average value of IDC. And so, yeah, that's what I've mentioned here. The lumpiness in this IDC curve is due to the discrete nature of electron charge. And so, which is something that is non-ideal as compared to the graph on the left. All right, so the short noise expression is, and so that's what introduces, or that is the main cause for short noise, and the short noise expression is 2Q times IDC multiplied by the bandwidth. So Q is the charge of an electron, B is the bandwidth. You could also write it as delta F. And what this expression tells you is that if you want lower short noise, then you could have electrons that have lower charge, because in such a case where electrons have lower charge, then your granularity or your resolution increases, right? So you won't have as big of steps as I've shown in this graph here. So theoretically, if you had electrons that had lower charge, or I mean lower Q, then you could decrease the short noise. And also, if you decrease the DC current or the bandwidth, that also reduces the short noise. Now, there are two important conditions for the presence of short noise. Number one is that there should be a direct current flow, and number two is that there should be a potential barrier through which the charge carriers, let's say electrons or holes or whatever, have to hop through. So there should be, again, I repeat, the potential barrier, there should be a potential barrier through which the charge carriers have to hop through. Okay, so short noise does not exist in linear resistors, or like short noise doesn't exist in ordinary resistors. Why? Again, look at condition number 2. There should be a potential barrier over which the charge carriers have to hop, and there are no potential barriers in a resistor, and so there is no short noise in resistors. Now, what about BJTs? Well, there are two potential barriers, right? Over here and here, and so short noise is a concern for if you're designing with BJTs, but it's again, it's not short noise is negligible for MOSFETs, and so that's again because no potential barriers. And you might think like, well, okay, what about this over here and this over here? We have N plus region and P minus region, and what about the potential barrier over here? Well, I want you to remember that when you have a transistor which is in saturation, you're basically inverting the layer. And we said that we have this inversion layer over here, which was originally P plus, sorry, P minus, but then when you put the transistor into inversion and strong inversion, this region where electrons flow through becomes N minus or even N plus, depending on how strong the inversion is. And so the inversion layer, what an electron sees, let's say if this is the drain and this is the source, right? And the electrons are flowing through here and they're going over here, then they don't see a potential barrier because all of it is just N plus, right? And so they don't see a potential barrier, which is why the short noise in MOSFETs is almost negligible, and it's not a concern. So that's pretty much it for short noise, and I'll see you in the next video. Bye-bye.